let's get started. So today we're going to talk about something that will seem kind of peculiar, but this material will prove useful later. Okay, so the topic is called orthogonal complements. And direct sums in Rn. Okay. I don't think we're going to get to direct sums, so mainly the topic is this thing called orthogonal complements. Okay. So we'll start off with something called orthogonal subspaces. It's a pretty simple idea. If you have subspaces of Rn, you have two subspaces of Rn, and we call them orthogonal subspaces if, what do you think? We'll call them orthogonal if what? If, yeah, basically if everything in X is perpendicular to everything in Y. Okay, so formally, if the dot product of X against Y is 0, oops, the number 0, for all X in X and all Y in Y, then we say that X and Y are orthogonal. Say that they're orthogonal subspaces. Okay. And we write X is perpendicular to Y. Okay, so pretty simple idea, right? We say they're orthogonal if every pair of vectors, right? Every pair of vectors in X and Y are orthogonal to each other. Okay, so for example, if I have X is the span of 1, 0, 0, and Y is the span of 0, 1, 0, and 0, 0, 1, then these subspaces of R3 are perpendicular to each other, right? These subspaces are orthogonal to each other. Because everybody, right, anybody in X is going to look like X, 0, 0. Anybody in Y is going to look like 0, Y, Z. Right? And if you take the dot product of these two vectors, you're going to get 0. Right. Okay, so these guys are perpendicular to each other. Notice that if I took Y to be, say, the span of just 0, 1, 0, those guys would also be perpendicular. So let me call this guy Y prime. That X and Y prime are also perpendicular to each other. Right? Anybody, right? This is, here I've got, on the left-hand side, what I have is, I have the X-axis, and then I have the YZ plane. Right? I have the X-axis, and I have the YZ plane. On the right side, I have the X-axis and the Y-axis. Over here I've got the X-axis and the Y-axis, and of course anybody on the X-axis is going to be perpendicular to anybody on the Y-axis. Okay. What if I have something like this? X is the span of 1, 0, 0, and 0, 1, 0. And Y is the span of 0, 0, 1, 0, and 0, 0, 1. So, in other words, right, x is the xy plane, and y is the yz plane. Do these count as orthogonal subspaces? So to be orthogonal, remember, to be orthogonal subspaces means that everybody in X is perpendicular to everybody in Y. Right? If you take anybody in X and anybody in Y, then they're perpendicular to each other. Okay. So the answer is no, right? Can you give me somebody in X and somebody in Y who are not perpendicular to each other? Connor, do you want to?
0, 1, 0.
0, 1, 0, yeah. 0, 1, 0 lies in both spaces and is not perpendicular to itself, right? You're not perpendicular to yourself unless you're the zero vector. Right, so right, 0, 1, 0 dotted against 0, 1, 0 is 1. Right, so the answer is no. Right, so this is a non-example. Okay. Another example. The null space of A. So suppose you have some matrix, an n by n matrix, and you're thinking let X be the null space of A and let Y be the range of A transpose. Y is the range of A transpose. Okay, so right, you have some matrix A1, 1, A1n, AM1, AMN, right? And you have the null space, right? And you have the range of A transpose. Okay. So I'm going to say that those guys are perpendicular to each other. So the null space of A actually is perpendicular to the range of A transpose. Right. X is perpendicular to Y. Okay. So why is that? Why does that make sense? Ethan.
Rehab of the range. Interesting.
The range, remember, is the span of the column space.
Okay.
Right, the span of the column space. It is the set of all outputs when you multiply that matrix by something.
Okay.
Right, so this is the span of the column space. Okay. Why does this make sense? Anybody tell me, Montana?
So the column space of the transpose of A is equal to the row space of A.
Yeah.
And the null space of A is any vector such that like A1 x1 plus A2 x2 etc. can only equal 0.
Yeah, okay, exactly. So you say, well, look, if I'm thinking about the null space of A, that is everybody who gets killed when I multiply by A, right? So null space of A, so x1 to xn is in the null space of A, means that this equals 0, 0, 0, 0, 0, right? Okay. right? Now the range of A transpose is the column space. Why did I say the span of the column space? It's the column space. Column space of A transpose, right? But that's the same thing as the row space of A, right? That's the same thing as the row space of A. And so what you see is that if you're in the null space of A, being in the null space of A means that you're perpendicular to every row, right? You're perpendicular to every row, right? This first row of A is perpendicular to X. Second row, when you take the dot product, you get 0, right? So being in the null space of A means that you're perpendicular to each of the columns of A, but that means that you're perpendicular to the whole row space of A, right? So anybody in the anybody in the null space of A is going to be perpendicular to anybody in the row space of A. In other words, the range of A transpose. So any x in the null space of A is perpendicular to any y in the range of A transpose, because this is the same thing as the row space of A. Right? And you know that, I'll say it again, right? You know that being in the null space means that you're perpendicular to all the rows, right? Anybody in the row space of A, I'm sorry, in the null space of A is perpendicular to each A sub I, right? To each of the rows of A. But if you're perpendicular to everybody in the rows of A, then you're certainly you're perpendicular to everybody in the row space. This is kind of coherent, right? Let me write it again. Right. Anybody in the null space of A is perpendicular to each row of your matrix, right? Every row of A, right? But that is the same thing as saying that you are perpendicular to the entire row space of A, which is the same thing as the column space of A transpose. So anybody who is in the null space of A is perpendicular to anybody in the range of A transpose. Okay, is that okay? Sorry, it was a little bit not clear. Okay, so that is orthogonal subspaces, and the second idea we're going to introduce is orthogonal complements. So let S be a subspace. Let S be a subspace of Rn. Okay. We define S perp. We define S perp as all the vectors in Rn such that those vectors are perpendicular to S for all S in S. Okay. In other words, the collection of all vectors that are orthogonal to every element of S. The collection of all vectors that are orthogonal to every S in S. Okay. And we call this thing the orthogonal complement of the subspace S in Rn.
So would you write in parentheses there
The collection of all vectors that are orthogonal to every S in S. Sorry, in an old math textbook, I saw that they had spelled collection with an X, and I thought it was so cool that I've always used it since then. It was like from the 19th century. So people used to spell collection with an X. Okay, so let's go back to, let's come to this example that we have here. Okay, so here we had, remember here we had the x-axis, right? And we had the YZ plane. We also had the x-axis and the y-axis, right? The x-axis and the y-axis. Okay, and these were both, in both cases, we could say that these things were orthogonal subspaces. Okay, but you see, it's not exactly the same thing. If we look, suppose we look at x perp. Okay, what is x perp? What is x perp? Well, x perp is going to be the collection of all vectors that are perpendicular to everybody in X. Right? The collection of all vectors that are perpendicular to every vector in X. Right? So is this x perp? No, right? Because it's part of it, right? It's part of it, right? These are some of the vectors that are perpendicular to everybody in X, but that's not all of them. In fact, this y is x perp. Okay. This guy, so this y actually is x perp. This y prime is not x perp, right? Right? X perp has to be the collection of everybody, right? It's all vectors that are perpendicular to X, to everybody in X. Okay, so we missed out on some of them in this for y prime. Okay, does that make sense? Abba? Okay, related to this, if you know that x and y are perpendicular to each other, then what can you say about x perp and y perp? If you know that you've got orthogonal subspaces, well, what does that tell you? turn to somebody nearby and say, it tells you squat. No, it tells you, I know, it tells you what? Okay, so what does it tell you? What does it tell you? Ethan?
It tells you that the x or y is a part of x or y, because you don't know that they're all, the example before, we know that x and y were perpendicular, but y didn't cover all of. So just, does it tell you that x is in y perp?
X is in y perp, and y is an x perp. And that's it. That's all you can say. Exactly. Right. Yeah.
Is it a subspace?
Yeah, these are all subspaces. Well, wait. What are you asking? Is X
Is X a subspace of Y perp?
Yes. I mean, so X and Y are subspaces to begin with.
Mm-hmm.
So, and yeah, so it's still a subspace. It is a subspace. But, a second set of questions. So, I'll do that one first. So, actually, let me work up to that. So, some simple observations. So, observation 0 is that S and S perp are orthogonal to each other. Okay, so that's trivial, right? To be orthogonal to each other, it means that everybody in here must be perpendicular to everybody in here, but that's how we constructed S perp. Right? S perp consists of all vectors that are perpendicular to S. So this is a tautological statement. Observation number 1, that if two subspaces are perpendicular to each other, then their intersection is, two subspaces are perpendicular to each other, then their 0 will be the 0 vector, right? Because if some vector lies in the intersection, that means that that vector must be perpendicular to itself, right? Right? Wrong time?
I was going to ask the 0 vector.
Yeah. So you see why the dot product of itself, again, the dot product against itself would be 0. This is the same thing as the magnitude of the vector squared. Right? And so you see that the magnitude of your vector would be 0, so it's a 0 vector. Right? Observation number 2 is that any orthogonal complement is a subspace. So the orthogonal complement of a subspace is itself a subspace. So I want you to take 1 minute and explain why that is to yourself or to somebody nearby. Okay, talk to somebody. Okay, so this is also pretty straightforward. Like to show something as a subspace, you need to show it's closed under addition and and scalar multiplication. You say, okay, well, say that you have two guys who are both in Y perp, right? In other words, x1 and x2 are perpendicular to everybody in Y. Right? But then it's pretty clear that x1 plus x2 is still in Y perp, right? Since x1 plus x2 transpose y is the same thing as x1 transpose y plus x2 transpose y, which is 0 plus 0, which is 0. Right? Straightforward. Okay, so there's a second part, right? You need to show that if x is in Y perp, then alpha x is in Y perp. But that's done basically the same way, so I'm not going to do it. You need to show closure under scalar multiplication as well, but that's pretty straightforward. Okay, so a bunch of simple observations. Something a little bit more complicated is this theorem that the book calls the fundamental subspaces theorem. The fundamental subspaces theorem, and it says this, that suppose you have an n by n matrix, then the null space of A is actually the orthogonal complement of the range of A transpose. The null space of A is the orthogonal complement of the range of A transpose. We basically did this already, but let me sort of say it again. And also that the null space of A transpose is the range of A orthogonal complement of the range of A. Okay, so that's just a trivial consequence. You replace A by A transpose, right? The null space of A transpose is the orthogonal complement of the range of A transpose transpose, which is just A. Okay, so let me do the proof. So we want to show that these guys are the same set. So we'll show that each is contained in the other. Right, that if you're in here, then you're in here. If you're in here, then you're here. Right? To show sets are equal, you show that they contain each other. Right there. Right? If you want to show A equals B, you show A is inside of B and B is inside of A. Show this. Show both of these things. Okay. So say, okay, well, let's say that X is in the orthogonal complement of the range of A transpose. That means that X is perpendicular to any vector in the range of A transpose. Right? So that means it's perpendicular to any column of A transpose. Right? Because the columns of A transpose are in the range of A transpose. But that means it's perpendicular to any row of A, but that forces AX to be 0. In other words, so X is in the null space of A. And to do the proof in the opposite direction, you just note that these arrows go backwards. All of these arrows go backwards, right? If AX equals 0, that means it's perpendicular to any row, and that means it's perpendicular to any column of AT, that means it's perpendicular to anybody in the range of A transpose. In other words, it's there. Okay. So just reverse the arrows. Yeah, Connor.
What's the notation that you use right after the proof?
Oh, this is, so I'm showing two parts of the proof. There are two parts to it. I want to show that this thing contains this thing, and that this thing is contained in this thing. So it's the set notation, right? Right. I'm trying to show that this equals this. So there's two parts to that. I need to show this, and I need to show this, right? That this guy is contained in here, and that this guy is contained in here. So it's just like, if I have an if and only if statement, then I sometimes will write this, right? We prove the forwards direction, we prove the backwards direction. Right? This proof also has two parts. Okay, so this is the fundamental subspaces theorem. It's not particularly interesting, but we will use it. It's a statistic tool. Okay, let's go on. More not exciting facts about orthogonal complements. Okay. Okay, great. I have time to do it. So let S be a subspace of Rn. Part 1 is that the dimension of S plus the dimension of S perp equals a number. What number? Sorry, what?
I guess this is dimension of S times 2. I don't know.
The dimension of S times 2. So you're saying that these guys will have the same dimension? S and S perp will have the same dimension? And?
The dimension of the particle.
The union of S
Yeah, N is the answer. N is the answer. That's right. The sum of the so the dimension of S and the dimension of S perp add up to N. So remember we had this guy right here. Right? You see that X is one-dimensional, X perp was two-dimensional, those add up to 3. 3 is the dimension of the ambient space. Okay. Part 2 is that if x1 through xr is a basis of S, and xr plus 1 through xn basis of S perp, then you can just amalgamate them into one big thing that is a basis of Rn. Okay, so if you have a basis of S and a basis of S perp, then the union of those two bases gives you a basis of Rn. So I'm going to have you do this as an exercise, hopefully both parts of it, if there's enough time. But before I let you try part 1, I want you to answer the question, what does this remind you of? The rank theorem, right? This reminds you of the rank theorem. Dimension of something and the dimension of something equals n. Okay. Right? Remember the rank theorem, right? If A is an n by n matrix, then the dimension of the nullity plus the dimension of the plus the rank equals n. Right? Dimension of the column space. So take a couple minutes and see if you can use the rank theorem to prove this statement. Okay. So you have this tool. See if you can use it to get this result.
In that case, when you're in the dimension of the range of it,
Yeah.
equal to the.
Right, because you have the dimension of you have the nullity plus the rank is equal to n. The rank is the same thing as the dimension of the column space or the row space. Right? You remember that the dimension of the row space and the column space are the same. Okay, turn to somebody nearby and say, here's the idea, or here's what we're going to do.
Transpose of the
Okay, so we want to use the rank theorem to prove this statement about the dimension of S and S perp. Right? The rank theorem is a statement about a matrix. Right? So what matrix are we going to use? Right? We need a matrix to get information here. What matrix?
N by N.
N by N, some N by N matrix. Any old N by N matrix. It's got to be.
Identity matrix?
Not the identity matrix. Somebody is saying it? Basis. Basis of Rn. All of Rn. Any basis of Rn? Wait, we want to say thing about S. Let's take a basis of S, right? Take a basis of S. So let A be let x1 to xr be a basis of S, and let A be the matrix with those as its columns. Right? It is an N by R matrix. Then the rank, then S, of course, is the range of A. Right? Because the range of A is the span of these columns. Right? This is the basis of S. S is the range of A. S perp is the range of A perp. At this point, what do? We use something that's up there, right? Range of A perp is the same thing as the null space of A transpose. By the fundamental subspaces theorem. Okay. And then you say, okay, now by the rank theorem, we see that the dimension of NA transpose plus the dimension of RA transpose equals N, right? Because A transpose is a R by N matrix, right? A transpose is an R by N matrix. You apply the rank theorem to A transpose. Right. Now, the dimension of RA transpose is the same thing as the dimension of RA, right? The dimension of the row space and the column space are the same. Remember that? Right. But this thing here is S perp, and this thing here is the dimension of S. So I'm going to take an extra minute or so and go through the second part of the proof here. So suppose you have a basis of S, suppose you have a basis of S perp, then those two sets, the union of those two sets is the basis of Rn. Okay. So the proof is that it suffices to show that these guys are linearly independent, right? Because there are n of them, and we're in Rn, so we don't have to prove spanning and linearly independent. We just need to show one or the other. So suppose that C1 x1 plus CR xr plus CR plus 1 xr plus 1 plus Cn xn is the zero vector. Okay. We'll do something funny and move everything, all of these guys to the other side. C1 x1 plus CR xr equals negative CR plus 1 xr plus 1 Cn xn. Okay. Let's call this thing V. Okay, whatever it is, let's call it V. Now V is in S, right? Because V is the sum of these guys in S. But V is also in S perp, right? Because these guys are all in S perp. Right? So that tells you that, so V lies in S, and it also lies in S perp. But the intersection of S and S perp is 0. Right? Okay. That tells you that C1 x1 plus CR xr equals 0, and CR plus 1 xr plus 1 plus Cn xn also equals 0. Right? So what? These guys equal 0, so the sum of this linear combination of the xi's from I equals 1 to r equals 0, so remember these guys are the basis of S, so they're linearly independent, right? And so all the coefficients are 0, right? So C1 through CR are all 0. And similarly, CR plus 1 through Cn are all 0 also, right? And so we have that the union of these two sets is still a basis. The union, right? We show that these guys are linearly independent, and so they form a basis. So x1 through xn are linearly independent, and thus do form a basis of all n. Okay, that's it for today. Unless there are questions. Anybody have questions? That's it for today.